Okay. All right, so in the first investigation, the very first thing that you are asked to do is you were asked to graph y equals 2x plus 1. So we were able to graph that on the patty paper. And then the next thing that you were asked to do in step 2 was graph the line y equal x. Hopefully you notice that every point that falls on this line y equal x has the x and the y value being the same. So that was what you were supposed to notice there. The x and the y value are the same no matter where you are on the line, y equal x. Then you were to reflect this original line, y equal 2x plus 1, across y equal x. So you're going to get this line, and hopefully you notice that these points, for example, those points, where they go on the reflected image. Now, once you have 2 points on the reflected image, you can write the equation of that line. So for part 9, on the original one, you should have been able to get this equation. So that is the equation of this green line, which is the reflection of the red line across the line y equal x. You should have been able to obtain that by looking at the 2 points and then writing the equation of the line, finding the slope, finding the y-intercept, etc. What did you notice? In number 7, you were asked to make 2 tables of values. So if you were to compare the points on the original line to the points on the image, the reflected line, what did you notice was the relationship between the domain and the range values of those 2 tables? Did anybody recognize anything? Now would be the time to answer the question.
The x and y intercepts are the opposite for each other. Well, they're kind of flipped, so.
Okay, so we don't use opposite because that means we're changing sign, right?
Yeah, it's not opposite on it.
Flipped because that's not math, but your idea is correct. The x and the y values are interchanged. The x and the y values are interchanged. So that means the domain values of your original function become the range values of your reflected function across y equal x. So that's what you were supposed to notice. So if you created a table of values, no matter where you are, so if I look at this one, if I look at the corresponding reflected point across y equal x, what should it be?
Anybody? 2 1/2.
2 1/2. And is that true? Yes, it is. If I actually get there. 2 1/2. Slowly but surely there, it's there. Okay, so that was what you were supposed to recognize, that the x values in the original function become the y values in the image function, the reflection across y equal x. And this relationship occurs when you are reflecting across y equal x. So you should have been able for number 8 to notice that the x-intercept is, related to the y-intercept of the reflected function by interchanging the x and the y values. Now, for number 10 on investigation 1, is the image of y equal 2x plus 1 reflected across y equal x? So is this line a function?
Yes.
How do you know?
Because each x value only has one corresponding y value.
Beautiful. And graphically, it passes the vertical line test. Excellent. All right, so let's look at investigation 2. Investigation 2 had you start with the parent quadratic function, right? Y equals x squared. We are again reflecting that across y equal x. If you were doing this by hand, you had to be very careful here. So if I'm reflecting this across y equal x, this piece here goes there. This piece here goes there. So does everybody see how this is the reflection of this parent function across the line y equal x? Again, if you were to make tables of values, you would be able to see that certain points, well, it would be more obvious if you use integer values, but your domain and your range values are interchanged from the original function to your reflected function, reflection across y equal x. Again, you have to pay attention to the plus or minus, right, when solving for x, or solving for y when we interchange the domain and range. And the only points that are fixed points are points that actually fall on the line y equal x. Because if you were to interchange in the x and the y values, they'd be the same. So those 2 points are your fixed points. Now, if I look at the reflection of this function across y equal x, is the image function, is the image a function?
No.
It doesn't pass
No.
the vertical line test, so it is not a function. Excellent. Okay, so let's go ahead and look at the third investigation. The third investigation asks you to look at the parent cubic function, y equals x cubed. If I reflected that across y equal x, notice what's happening. I have this piece, which is now going to be reflected, and it would look like this. Oh, interesting. Since this is a cubic function, we're then going to be taking the cube root, and since the root index is odd, I don't have plus or minus, right? Because I can take the cube root of a negative number. So hopefully you were able to see, oops, where is it? This reflected image. Is that a function? Is the image, the graph of the image of the reflection of the original parent cubic function a function?
No.
It's not? That's
I'm-
not a function?
Yeah, yes,
It is
that
a
is a function.
Wait,
It-
sorry, I was looking at it wrong. Sorry, I thought that the point it crossed was. Never mind.
That's okay. That's okay. So again, the only points that are fixed points are the points that actually fall on the line y equal x, because when I interchange my x and my y values, they're the same value. So that doesn't change. Now, if you look at the summary says in the three and this was the image of the first investigation. This was the image of the second investigation. This was the image of the third investigation. Out of those, which of the original functions had images that were functions? Did that have an image that was a function? Did that have an image that was a function? And did that? Which?
Investigation 1 and 3.
The first one and the third one. So y equals 2x plus 1 and y equal x cubed, but not y equal x squared. So what would you have to do to a function whose image was not a function to make it a function? What would I have to do to this image to make it a function?
Reflected on the x-axis.
Reflected along the x-axis, I would get the original. What would I have to do to this to get it to be a function?
Reflected on the y-axis.
Well, if I reflected across the y-axis, I would just be
Reflects
facing.
across the x and then the y.
Okay, then that would just be around the origin. So that would just give me up and then over. So it would give me right back here, right? So you'd have to reflect it about y equal x or y equal negative x. That would be the answer. Now, we already talked about number 3, the images of the points of the original functions that intersected the line y equal x being the only fixed points that don't change in both the original function and the image. So what do you think is going to happen in number 4 of the summary if I take y equal 4 and I reflect that across y equal x? What is the image going to be? Can you give me the equation of the image?
X equals 4.
Beautiful. X equal 4. And is the image a function?
No.
No. So this horizontal line becomes the vertical line. The only point that is on the original and the reflection across y equal x is the point that falls on y equal x. So again, the relationship between a function and its inverse being the reflection across y equal x, is that the domain and the range are interchanged. So the domain of the original function becomes the range of the image. The range of the original function becomes the domain of the image. So in number 5, is the inverse of a function always a function?
No.
No, and we just saw that with this example. It is not. So, you know where this is going. We love true, false, multiple choice questions that make you think. Is the inverse of a function always a relation?
Yes.
Yes, because relations are just pairings of input and outputs, but not all relations are functions, only if they have one output for each input. So, can you name 2 functions that are their own inverses? 2 functions that are their own inverses.
Y equals X.
Okay, that is one, because y equals x is, in fact, if you reflect about itself, it stays the same. Do we have another one? Can anybody think of another one?
Is the parent rational function 1?
Okay, so what would that be? Y equals, what's the parent rational function?
1 over X.
Is the reflection across that? Well, the image would be x equal 1 over y. Oh, look at that. You're so clever. What else? Anyone else come up with another one? That was beautiful. Austin, that was beautiful.
Isn't it like absolute value function?
Well, if I take y equals the absolute value of x, right? Let me remove this one. And then I take x equal the absolute value of y, right? Because I'm just interchanging domain and range. Oh, they're not the same.
Y equals negative X.
Y equals negative x. If I reflect that, it would be x equal negative y. It's the same thing. Beautiful. Excellent. Okay, good job, good job, good job. All right, so hopefully this has geared you up so that you can geometrically appreciate the fact that the reflection of a function across the line y equal x is just the interchanging of the domain and the range values. So easily to obtain the equation of the reflection of the original function is just to interchange the x and the y values and solve for y. So that is one quick, easy way for you to be able to obtain the equation. So I don't know if you were able to figure that out, but it's quite nice. So again, the reflection across y equal x is taking the inverse of a function. The inverse of a function is not necessarily yielding an image function. So the result of reflecting across y equal x doesn't necessarily produce a function. It's a relation, but not a function. Any questions on that investigation? No?
This is just out of